What's a pixel? So here's a picture, right? This is a picture. Or sorry, this is a picture here. So if we focus just on this part here, it looks like this, right? Okay? And this, the whole picture, including this part, is made up of pixels. So here's a so each one, there's a pixel, there's a pixel, these are all pixels. Okay? Now, if it's a black and white picture, then the pixels are only going to be what colors? Between shades of black and white, right? Gray. Right? If it's color, what they usually have is they have a blue part, a red part, and a green RGB. R, red, G, green, B, blue. Blue, red, green, blue parts separately. Okay? And they're going to be different intensities of the red, different intensities of the blue, and different intensities of the green. Let's just think about it right now as it's black and white. Okay? So you have a pixel here, and then a pixel next to it, and then a pixel next to it, and a pixel next to it, right? And each one of those is a certain shade of gray, and so it can be represented by a number, like usually a number between 0 and 256. So 256 might be, I don't know if it's all white or if it's black, but it's one or the other. And then 0 would be the opposite one. Okay? Everyone get it? So that's a pixel. So what we're trying to do is image recognition, right? And at its very base, it's just a bunch of pixels. Right? So I have a pixel here, a pixel here, a pixel here, a pixel here. Right? So let's suppose that there were 20 by 20. The size was 20 by 20. So that would mean how many pixels altogether? 400, right? 20 by 20. Right? So what we do in a neural network in this situation is, how many inputs did we have in the last example? 3, right? We had 3. But in this scenario, if we had a 20 by 20, we'd have 400 inputs. 1, 2, 3, 4, all 400 of them. And each one would be what? An input of a number between 0 and 256. Right? And that in that way, we'd be representing the entire image. Right? And then, somehow, we're supposed to get the computer to know that that is an 8, or that is a 7, right? Because we're going to have a picture of a hand-drawn 7, and we're going to split it up into all these pixels. Now you can see why it's so hard. Right? We're just going to feed the computer 400 inputs of different shades of gray. And the computer is supposed to go from that to saying, oh, that's a 7. Right? It doesn't sound particularly like an easy problem. Right? But that's the kind of information we can provide the computer. Otherwise, what else are we going to provide it with? Well, maybe you might come up with some other kind of ideas, like whether there are circles in it or not. I don't know. I don't know what we could do, but that's the way it's done at its base. Okay? So, let's go back to here. Suppose we have a network of perceptrons, these things, that we'd like to use to learn to solve some problem. For example, the inputs of the network might be the raw pixel data from a scanned, handwritten image of a digit, like we just said. We'd like the network to learn weights and biases. Now, we already introduced the idea of the bias, which is what? It basically was the threshold, right? The bias was the threshold, negative the threshold, so we already introduced that as well. So what we want the computer to do somehow, the inputs are not up to the computer, are not up to the model, right? The inputs are the image. So that has nothing to do with the model, right? The model has to just accept those as what they are. But what the model can vary is what? The weights, right? The model can vary the weights and the bias. Okay? So we'd like the network to learn weights and biases so that the output from the network correctly classifies the digit. So we're going to send in a picture of an 8, but it's going to be a handwritten picture. It's just going to be the bunch of pixels. And we want the computer to say, oh, that's an 8. Right? We want it to classify this image as an 8. We want it to classify this image as a 7. Right? We want it to, right? Depending on the image, we want it to classify it between 0 and 9. Right? Okay? So, we'd like the network to learn the weights and biases so that the output from the network correctly classifies the digit. Okay? Now, we haven't discussed anything about learning, how it learns at all yet. But anyway, that's where we're heading. So, to see how learning might work, suppose we make a small change in some weight or in some bias. So we have these weights here. Suppose we made a little change in one of the weights. Okay, is this clear? We're going to change some weight by delta W. Okay? Everyone understand that notation, delta? Delta just means a change. What we'd like is for the small change in the weight to cause only a small corresponding change in the output from the network. Okay, we don't want to have a small change in W result in a big change everywhere else, because that's going to mean that, like, it's not going to work well, actually. If just a small change in W makes a big change everywhere else, then it's unlikely that our network will be able to do the right job of classifying. Okay? So we want a small change in W to result in only a small change in the output. All right? Everyone follow so far? Suppose the network was mistakenly classifying an image as an 8 when it should be a 9. We could figure out how to make a small change in the weights and the biases so the network gets a little closer to classifying the image as a 9. And then we'd repeat this, changing the weights and biases over and over to produce better and better output. And then we would say that the network was learning. And the question is, how are we going to change the weights? Now, that was a problem that people were working on for a long time. You know, a lot of people spent a lot of time thinking about it, how to change the weight. Obviously, the amount that you change the weight has to be something to do with the output. In other words, the output said it was an 8, but it was actually a 7. And actually, it doesn't say that it was an 8. It works more like it says the probability of 8 was 60, and the probability of 7 was 50, or something like that. Maybe that doesn't make sense, but, right? It gives like a probability, and so you want to adjust those probabilities, right? So it said it was probability, it's actually an 8. We put it in, and it says it's a 7. It says the probability of 7 is a little bit higher than the probability of 8, right? So how are we going to adjust the weights from that stuff, from that scenario? So this said higher probability of 8, let's say 60% of 8, and 50, maybe those numbers don't make sense. Let's say 40% that it was an 8, and 30% that it was a 7. No, the other way around, sorry. 40% that it was a 7, and 30% that it was an 8. And it's actually an 8, but it's making a mistake. How are we going to take that 10% difference and somehow change the weights so that it does better next time? Anybody have any suggestions? This is the problem that I'm sure I'd say, I don't know the history actually, but they spent 20 years trying to think about it. And probably a lot of people would. Trial and error. What do you mean by that? repeatedly experimenting. So, I don't think that's right. Anyway, I can't say. I couldn't figure it out myself. But it turns out that they're going to use the chain rule for this, actually. Yeah, you'll see. We're going to use the chain rule to do it. And that, I guess, was a pretty big development. So anyway, you can see the issue, right? It's pretty tricky how to adjust the weights, right, to get them to somehow reflect the fact that there was a certain amount of error in the output predictions, right? That's a pretty tricky thing to figure out how to do. Anyway, then we'd repeat this, changing the weights and biases over and over to produce better and better output. So we'd adjust the weights, and then we try it again. And then sometimes there's going to be an error, and so we'd have to adjust the weights again. And then we do it again and again and again and again and again, each time adjusting the weights, and that's what they call learning. That's called learning. Adjusting those weights and the biases is called learning. Okay, that's the network learning. Okay? In fact, a small change in the weights or bias of any single perceptron in the network can sometimes cause the output of that perceptron to completely flip, say from 0 to 1. So now they're not talking here about using probabilities. They're talking about just a threshold. There's just going to be 0 or 1, I think. So anyway, it's just, so if you're not careful, the system is going to be, if you just make a small change in a weight, it's going to make a big change in the output. That we want to avoid, but that's not necessarily easy to avoid, is what they're saying here. Okay, so the introduction of the sigmoid neuron helps to solve this problem. And we already talked about what the sigmoid neuron is going to be. What's the point of it? What are we going to do? We're going to take the input and pass it through the sigmoid curve. And somehow that's going to help, right? Not clear exactly why, but it's going to help. The introduction of a so-called sigmoid neuron will help solve this problem. Just like a perceptron, the sigmoid neuron has inputs like this. But instead of just being 0 or 1 inputs, first of all, we're not stuck with just 0 or 1 inputs anymore. These inputs can take any values between 0 and 1, so this would be okay as an input. Also, just like a perceptron, the sigmoid neuron has weights, so we also have weights here, and an overall bias, but the output is not necessarily just 0 or 1. And why is that? You can confirm that to me because you understand something. Why won't it just be 0 or 1 anymore? Because the output is coming from where? The sigmoid curve, which is not necessarily 0 or 1, right? It can be anything in between 0 or 1, right? Okay, so the output is not just 0 or 1. So some books use a Greek letter for the sigmoid curve, and so you have it like this. And we're going to put the input of a neuron into this sigma. So the input, remember what's going to go into the sigmoid curve? The inputs, right? And what are the inputs? How can we express them? We already said we can express them compactly like this. Why? What does this mean? It's the dot product. So that's the weights times the inputs plus the bias. Okay? So that's going to be the input, right? So we're going to put that into here, right? Into the sigma curve, right? Into the sigma function. So we're going to put that over here, in other words, right? So it's going to be here. Okay, so instead of this, we're putting in this, our input, so that this should go here. In other words, it should look like this. This just is another way of writing E. We write EXP because this is just easier. You don't have to use superscript. So it's easier to type. That's all. Physically easier to type. That's all.
So instead of using e to the superscript, they just use exp. Okay, because it's all one line. But what's going in there is this. Okay? Is that clear? It's really not that complicated. It looks pretty complicated. But we're just putting the input into here, which is what we said we wanted to do. Is that clear or not? Let's go back and make sure. What are we doing? We're taking these times their w's, and they go into here, right? And then we're passing that into what? Into into the sigmoid curve. And what's the function for the sigmoid curve? This is it. So we're passing it into here. So what does that mean? We're putting it in here. So that means we're putting it in here. So that means it's here. Okay? So what's the difference between this? So, okay, does everyone follow so far? The next question is, what's the difference between doing this and the perceptron? What are the consequences of doing it this way as opposed to perceptron, which we said is only going to output between 0 and, is only going to output 0 or 1, right? So this, first of all, is not just going to output 0 or 1. We just said it can output anything between 0 and 1. So that's one consequence. Yes? Sorry?
Related to this fact that we can have values from 0 to 1. When we have a change, it's not going to be as dramatic as
right.
from 0 to 1, but like it can be from 0 to 0.20, and it's not as dramatic as.
Can you say that again?
It's like before we had, if there was a small change in the weights, we would have a change from 0 to 1. But like now we can have changes even in between. So
right.
The change is going to happen, but it can be smoother.
She got it. I didn't quite get that. Right. That's right. Yes. So she said just now, so what's the difference between this and the perceptron? And we said, just in the previous slide, that we wanted small changes in the weights to produce not huge changes in the output, not big flips. We don't want to flip between 0 and 1. And with this, as she just said, we can get a more graduated change, right? Because it's a smooth curve. So instead of this situation where as soon as we pass a certain value it jumps up, we get, if we just move a little bit this way, we only get a slight change in here. Yeah. Right. Versus, sorry? Yes, right. Right. Okay. So, that's the point, yeah. So if z is, and also, a few other observations are that if z is a large positive number, that is, if the input is large positive, way out here, then this is going to be close to 1. So that's good, because that was the same thing with the step function. When we get a large number here, we get 1. When we get a small number, we get 0. So it conforms to that, or it's similar to that. And if z is large negative, we get 0. It's only when this z, the input, is of modest size that there's much deviation from the perceptron model, right? The perceptron model just jumps, but this one is kind of smooth in this area, right? Okay. Okay, any questions? So if sigma had in fact been a step function, then the sigmoid neuron, so if it was a step function, then the sigmoid neuron would just be a perceptron. Okay, so the only difference between the sigmoid neuron and the perceptron is that this perceptron uses this, and the sigmoid neuron uses this. Okay? So we didn't say it explicitly, but we could represent what was going on in the perceptron as this function. But in the sigmoid neuron, it's this function. Since the output would be 1 or 0 depending on whether it's positive or negative.
then they say, actually, anyway, let's ignore that. By using the actual sigma function, we get, as already implied above, a smoothed out perceptron. Indeed, it's the smoothness of the sigmoid function that is the crucial fact, not its detailed form. The smoothness of the sigmoid means that small, and this is what we just said, small changes W in W sub j in the weights, or the bias, will produce a small change in the output. Right? That's what we just said. Okay? Okay, good. In fact, calculus tells us that the output is well approximated by this. Now we won't worry about this. But the meaning of this is that the output is a linear function of the changes in delta in W sub j and B. So it's linear means that if you make a small change in here, you get some kind of, well, proportional change in here as opposed to a big jump. Right? Linear means that if you make it, if this goes from here to here, the change goes only from here to here. It doesn't jump up somehow. Or that's not what linear means, but that's a consequence of linear. Okay? This linearity makes it easy to choose small changes in the weights and biases to achieve any desired small change in the output. So while sigmoid neurons have much of the same qualitative behavior as perceptrons, they make it much easier to figure out how changing the weights and biases will change the output. Okay, now one more thing. We call that sigmoid function the activation function, and we're not really stuck with sigmoid functions. We can use other ones, and people have experimented with other ones as well, but they should generally have that shape. But there are other functions that have that shape as well. Or they should have certain properties anyway. And but anyway, the sigmoid one happens to work very nicely, but people want to improve the neural network performance, and they're experimenting with other possible functions and hoping that they might get better results. If it's the shape of sigmoid, which really matters, and it's not the exact form, then why use the particular form used for sigmoid in the last slide? In fact, later we may occasionally consider neurons where the output is like this for some other activation function. So we may not use the sigmoid function. Okay? How should we interpret the output from a sigmoid neuron? Obviously, one big difference between perceptrons and the sigmoid neurons is that the sigmoid neurons don't just output between 0 and 1. They can have as output any real number between 0 and 1. So these values are okay. This can be useful, for example, if we want to use the output value to represent the average intensity of the pixels in an image input into a neural network. But sometimes it can be a nuisance. Sometimes we want the output from the network to indicate either the input image as 9 or not 9. Obviously, it's easiest to do this if the output was a 0 or a 1, as in the perceptron. But in practice, we can set up a convention to deal with this. Remember, this is like the cutoff value that we saw when we were talking about naive Bayes. Right? We set a cutoff value, so if it's above a certain level, we do this. If it's below that level, we do something else. So we do the same thing here. Nothing very ingenious about it. But in practice, we can set up a convention to deal with this, for example, by deciding to interpret an output of at least 0.5 as indicating a 9, and any output less than 0.5 is indicating not a 9. So that's just a technical detail. We don't have to get that technical, I guess. Okay, we've been discussing neural networks where the output from one layer is used as input to the next layer.
Such networks are called feed-forward neural networks. This means that there are no loops in the network, and information is always fed forward, never fed back. So I'm just bringing this up as a term so that you've heard what that term. So they talk about it as feed-forward, means that there's no back loop. So the input from here goes to here, and then doesn't come back and circle back and get, like some kind of loop. So they do work. So people are doing research in those kinds of loops, but they're not as popular now, at least not now. However, there are other models of artificial neural networks in which feedback loops are possible. These models are called recurrent neural networks. Okay, but we won't study those. Okay, so here's another picture of a neural network. And here we have 4 inputs. And then this layer is called the input layer. This is called a hidden layer. And this is called the output layer. Those are the typical terms. And the input layer just means the layer where the input variables go. So this would be x1, x2, x3, x4. Those are just the input values. So if we had the pixel example that we were talking about before, where we had a 20 by 20 image, how many of these green neurons would we have? 20 by 20, right? 400, right? So we'd have 400 here. Okay? And then we'd have a hidden layer here, called a hidden layer. It's just another layer. It's just a layer. And then we'll have an output layer. Okay, here's another one, a little more complicated. But I mean, we use much more complicated than this. Like, maybe we might have 10,000. And it doesn't matter. The computer's dealing with it, not us. Right? But the image it looks really complicated. Okay? Here's another simple one. 4 inputs. Hidden layer just 3. This has 2 outputs. So depending on what we're trying to do, we'll have different numbers of things. This is something, I didn't check out exactly what it was, but it looks like kind of trying to predict a prognosis about cancer. Okay, so we have like the stage that the person is in terms of their cancer, I guess, and did they have radical surgery or not? So that's like a yes-no variable, probably. I don't know what that means. 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 I don't know what. Okay, I know what age means. Okay, so these are all inputs, and then we get a prognosis. Are they going to die or not? Or something. I don't know what the prognosis is supposed to be. But we can use a neural network in this scenario as well. It doesn't have to be image recognition. Okay? Here's another one. Simpler one. This is just 2. And this is the one that we're going to study next time because it's pretty simple. And this is the one where we're going to study how to adjust the weights. How to go backwards and adjust the weights, because we want to make it as simple as possible, but not, if we only have 1, there's no way to adjust the weight, so we need at least 2. There's no weight adjustment if we just have 1, I guess. So anyway, this is about as simple as we can get. And that's the one we're going to use to talk about how to adjust the weights. And this is another picture of the same one, but it doesn't look like it's the same, because they broke it up into a couple of different pieces. So this is not the standard way that they write it. They don't usually break it up like this. The way they usually view it is like that. Okay, but we're going to break it up into several different blocks. We're going to have what? X times W plus B is the input, right? And then we're going to have, what's next? Then we're going to pass that into the sigmoid, so we're going to separate that. So we're going to take X, this is the input, so this is X, times W gives us this, actually. Okay? So this is the input times W, actually plus B, but we're ignoring the B. Okay? So that gives us this piece here. I'm not sure what to write it as X here. I would call this X, but he wants to use I to stand for input. Okay, so he's just saying Actually, this is kind of a peculiar thing to call that x. So just ignore this right here. So what do we get? We get the input times the weight here, and then we're passing that into what? The sigmoid function, and then we get something out. Okay, and then we pass that into the next node and do the same thing, right? Okay, everyone follow? So let's look at this, because this is the notation we're going to use to do the to figure out how to adjust the weights. And by the way, that's called backpropagation. It's called backpropagation, and it uses a very well-known concept of gradient descent, which we'll talk about. But that basically, we're just going to use the chain rule. That's all. Okay? Anyway, let's just check out this notation. So look, there's an IL, and there's an IR. There's a WL and a WR. So what the L and R stand for are left and right in this notation. So in other words, we're going to get an input here, and that's going to be called IL, and then an output here, and that's going to be called OL, okay? But then OL is going into here, so he also calls it IR. Do you understand the notation? Why is it R? This is the right, this is called the right neuron, and this is called the left neuron. Okay? So we're going to get IL goes in here, and then OL comes out here, right? Because this is the left neuron. Okay? Everyone get that notation? And then OL comes out here, but it also goes in here, so we'll also call OL is equal to what? IR. Right? Let's say it again. OL comes out here. Why is it called OL here? Because it's the left, L stands for left neuron, and it's the output of the left neuron. So that comes out, but it also goes in here, so that's called also I, the input, into the right neuron. So that's IR. So OL and IR are the same thing. So, where is that? Here. OL and IR are the same thing. Okay? Now what does PL stand for? So that's called the product. The product, why is it called the product? Because it's I times W. Okay? It's the product of I and W. Okay? Alright, so we also have a P here, because it's I times W. Okay, so everyone get that? So we've got an L, a W, a P, and an O in this drawing. Okay? It's not the standard notation for neural networks. Now, nobody else uses this. This comes from that MIT course. Okay, this is from the MIT course. But it's nice because it's easy to work with this to do the chain rule. Okay. So note that the subscripts indicate the layer. So by the layer, it means this is the first layer and this is the second layer. This is the left layer and this is the right layer. So the subscripts indicate the layer. Thus, IL, WL, PL, OL are the input, the input, weight, product, and output associated with the neuron on the left. And IR, WR, PR, OR are the input, weight, product, and output associated with the neuron on the right. Okay, of course, OL equals IR. Okay? All right, so we have this notation. Now, how are we going to, we're out of time, but we're going to ask, how are we going to judge how well we did? So what we're going to do is we're going to take our sample data, our training data, and we're going to take one element of it, one piece of it. We're going to send it through the network and send it through here. And it's going to make a prediction, right? And then we're just going to look at the difference between the prediction and the actual true value. Right? So we're going to look at how well it did as compared to the actual, what it should have done. And that's what this means. This is the desired or the true value, and this is the observed value. This is how well it did, and this is what it should have done. And we're going to consider the difference between those. And then for some mathematical reason, we actually square that, which is a standard process. It's basically, one of the main reasons is to get rid of cancellation. Because when you square things, it's all positive, right? So that's the main reason. But you could also take the absolute value to achieve that. It turns out that squaring mathematically is much easier to deal with. Like if you want to do the derivative, and you're doing the derivative of a square, something squared is much easier than the derivative of an absolute value. So for various reasons, much easier to square it. So they square it. And then they take a half, I don't know, half, no reason in particular. And that's called the performance function, how well we did. That measures how well we did, right? If we got very close to the desired output many times, this is going to be a small number. The performance is going to be small. So the smaller this is, the better the performance, except that he has a negative there, so it's like the opposite. But anyway, this measures how well we did. Okay, if you want to make it positive or negative, doesn't matter. Okay, so we're going to use this to determine how well we're doing, and then we're going to use this to determine how to adjust the weights, or how much to try to adjust the weights. So if we're doing well, we don't want to adjust the weights much, but if we're not doing well, we want to adjust the weights more. Right? So that's what we're going to do. This is called the performance function. Okay, so that's all. So I may give you some homework, so I'll announce it. I'll also publish this on our Blackboard this month. And also I'll put the video up. That's all you can go.